All right, let's get straight into this explainer. If you've been staring at your textbook feeling totally overwhelmed, take a deep breath. We're doing an ultimate rapid-fire revision of the first 4 chapters of your ICSE Class 9 Geography syllabus for tomorrow's exam. We're going to lock down the absolute essentials so you can walk in there and ace this paper.
Here's our game plan for today. 1. Our unique blue planet. 2. Mapping the geographic grid. 3. Earth in motion. And 4. Inside the Earth's structure. We're basically going to build a mental map together. We'll start way out in space, lay down the surface grid, set the whole planet spinning, and then literally slice it open to look deep inside. Let's go.
So, starting with Arc 1, our macro view from space, our unique blue planet.
First up, the actual shape of the Earth. Please do not get tricked on the exam by writing perfect sphere. The correct geographical term is a geoid, which literally just means Earth-shaped. It's technically an oblate spheroid. Why? Well, as the Earth rotates, it creates this centrifugal force that causes a slight bulge at the equator and flattens it out at the poles.
It really is wild when you look at the cosmic checklist that makes life here possible. We sit exactly 150 million kilometers from the sun, which is right in that perfect Goldilocks zone for ideal temperatures. Plus, we've got an atmosphere made of 21% oxygen and 78% nitrogen, acting like a giant protective blanket against UV rays. And of course, a fully active water cycle. Every single one of these factors has to be absolutely perfect to make Earth the only known habitable planet.
All right, zooming in now to Arc 2, mapping the geographic grid.
You know the exam loves those distinguish between questions, right? So let's break this down really clearly. Latitudes are your horizontal parallels. They actually vary in length, shrinking as you get closer to the poles, with the equator sitting right at 0 degrees. Longitudes, on the flip side, are vertical meridians of equal length that all converge right at the poles, starting from the 0-degree prime meridian. Remember, latitudes measure north-south and create our heat zones, while longitudes measure east-west and, super importantly, dictate our time zones.
Now here's a number you really want to burn into your memory for the multiple choice section. 111 kilometers. Since the Earth's circumference at the equator is roughly 40,000 kilometers, 1 degree of angular latitude distance is going to equal right around 111 kilometers.
So when you get those time calculation questions, here is the 3-step formula you need. Remember, the Earth rotates 1 degree every 4 minutes. Step 1. Find the degree difference in their longitudes. Step 2. Multiply that by 4 minutes. And Step 3. Apply the golden rule. If you're traveling east, you add time. If you travel west, you subtract time. Just remember, east gain, west lose.
Which brings us to that classic tricky question. Why do you lose a full day when traveling from Tokyo to Alaska? Well, this happens because you're crossing the international date line, located at the 180-degree longitude. And if you look at a map, you'll notice the line zigzags around islands in the Pacific. That's entirely intentional. It's drawn that way to prevent a single country from experiencing 2 different dates at the exact same time.
With the grid set up, let's jump to Arc 3, Earth in motion. Okay, here is a pretty staggering fact for you. Right at the equator, the Earth is rotating at 1,670 kilometers per hour. That is literally faster than most commercial airplanes fly. But, we don't go flying off the surface or even feel the speed. And that is entirely thanks to the invisible anchor of gravitational force holding us firmly to the ground.
You've got to keep these 2 primary motions completely separate in your head. Rotation is the Earth spinning on its own axis, from west to east. It takes about 24 hours, giving us our daily cycle of day and night, which is separated by the circle of illumination. Revolution, however, is the Earth actually orbiting the sun in an anti-clockwise direction. That takes 365.25 days, and it's exactly why we have leap years and seasonal changes.
But the absolute secret ingredient to those seasons is this number right here, 23.5 degrees. The Earth doesn't spin perfectly straight up and down. Its axis is tilted exactly 23.5 degrees from the perpendicular plane of its orbit.
What's really fascinating about this tilt is the massive domino effect it creates. Think about it. Without this angle, we wouldn't have summer or winter at all. Everywhere on Earth would just have equal 12-hour days all year round. But because of the tilt, we get unequal lengths of day and night, distinct heat zones, the creation of our seasons, and as a result, incredibly varying plant and animal life depending on what latitude you're at.
And now for our final arc, let's look at inside the Earth's structure.
I want you to take a mental screenshot of this table.
Let's categorize the three main layers: the crust, mantle, and core. Notice the huge differences in thickness here. The crust is this fragile layer just 5 to 60 kilometers deep, sitting on top of a massive 2,900 kilometer mantle. And then the core with a massive 7,000 kilometer diameter. This framework also breaks down the physical state and chemical makeup of each, which we're going to look at right now.
Starting right at the top, the crust is divided into two parts based on its chemical composition. Sial stands for silica and aluminum. It has a lower density and it's what forms our continents. Sima stands for silica and magnesium, which has a higher density and forms the ocean floor. And because Sial has a lower density, it literally floats right on top of the denser Sima layer beneath it.
As we go deeper, we hit the asthenosphere. This is a vital keyword for your exam, so definitely remember this one. It's the partially molten, semi-solid upper layer of the mantle, found at a depth of about 100 to 410 kilometers. The extreme heat and pressure here keep the rock in this semi-molten state, which is exactly what feeds the magma chambers of volcanoes up on the surface.
Now, as we move between these major structural layers, we hit these boundaries called discontinuities. The Mohorovičić, or Moho discontinuity, is the boundary between the crust and the mantle. Then there's the Gutenberg discontinuity, which is the boundary between the mantle and the core. And how do we even know they're down there? Well, these are transitional zones where primary and secondary seismic waves from earthquakes either dramatically change speed or just disappear entirely. It scientifically proves these different interior layers exist.
Finally, we reach the very center, knife. This is the Earth's core. It's composed of nickel, that's the Ni, and iron, the Fe, reaching just blistering temperatures of up to 6,000 degrees Celsius. Knife is incredibly important because the liquid iron in the outer core rotating around that solid inner core is exactly what generates the Earth's entire magnetic field. So I want to leave you with a quick thought experiment to really lock all this in for tomorrow's exam. What would actually happen if the Earth's core suddenly cooled down and hardened? Just think about it. Tectonic activity would completely halt, the magnetic field generated by that moving liquid iron would vanish, and without it, our protective atmosphere would just be completely stripped away by solar winds. It really shows how every single chapter we just covered is deeply connected. So review these concepts, get a good night's sleep, and best of luck on your ICSE geography exam tomorrow. You're absolutely going to crush it.